Welcome to our presentation on comparative study of machine learning algorithms for enhanced credit default prediction. In this session, we will delve into the world of loan classification and share our findings from a comprehensive analysis. Our study is based on a dataset collected from a reputable financial institution in Bangladesh, where loan management is a critical aspect of their operations. Accurate loan classification plays a pivotal role in minimizing financial risks for lending institutions, while ensuring that deserving borrowers are not denied loans. Throughout this presentation, we will explore the challenges, methodologies, and outcomes of our comparative study. By the end, you will have gained a clear understanding of which machine learning model is the most effective and reliable for loan classification. Let's discuss the importance of loan classification. Accurate loan classification is a cornerstone of responsible lending practices. The financial institution relies on loan classification to minimize financial risks. Inaccurate classification can lead to significant financial losses from defaults. Our work is essential to ensure fair and efficient loan processing, benefiting both borrowers and the lending institution. The drawbacks of manual process for loan classification are as follows. Manual loan classification is prone to human errors, subjectivity, and inefficiency. It relies on individual judgment, which can lead to inconsistent decisions and bias. Additionally, manual classification is time-consuming and may not effectively handle large volumes of loan applications, potentially resulting in delays and missed opportunities. The objectives are: achieve high accuracy in loan classification using machine learning algorithm. High accuracy ensures that loans are correctly classified as either bad or good, minimizing financial risks for the lending institution. Conduct a comparative study of multiple machine learning models. Comparing models helps us identify the most suitable one for loan classification, considering their strengths and weaknesses, ensuring robust and effective decision-making. Now let's review some literature. This paper studies the performance of several machine learning models for credit default prediction, using a unique and anonymized database from a major Spanish bank. The paper compares the statistical performance of a simple and traditionally used model like the Logistic Regression, with more advanced ones like lasso, penalized logistic regression, classification and regression tree, random forest, XGBoost and deep neural networks. The paper also examines the benefits of using machine learning in terms of predictive power, both in classification and calibration. This paper measures the model risk-adjusted performance of machine learning models for credit default prediction, using a dataset from a major Italian bank. The paper proposes a novel approach to adjust the predictive performance of machine learning models by incorporating the model risk, which is defined as the difference between the expected and actual losses due to model errors. The paper shows that machine learning models have higher model risk than traditional models, and that model risk can be reduced by using hybrid models that combine machine learning and traditional techniques. This article presents the performance of several machine learning models for loan default prediction, using a real-world dataset from a prestigious international bank. The article demonstrates that the XGBoost model can achieve a 100% accuracy for predicting loan default, outperforming other models, including XGBoost, random forest, k-nearest neighbors, and multilayer perceptrons. The dataset used in this study comes from a private bank in Bangladesh. The dataset was collected while taking privacy and ethical concerns into account. The dataset contains information about various aspects, totaling 14 pieces of information. 80% of the dataset was used for training and 20% for testing the model. We picked out the most important attributes for training and testing our model. These attributes include marital status, gender, education level, number of dependents, applicants' income data, self-employment status, loan amount term, loan amount, co-applicant's income, property area, credit history, and loan status. For our comparative analysis, we've selected 6 distinct machine learning models, each with its unique strengths and characteristics. The selected models are as follows. 1. Support vector machine. This is a versatile classifier that can handle complex data and find clear decision boundaries. 2. K-nearest neighbors. KNN is an instance-based learning algorithm that relies on the similarity of data points. 3. Decision trees. This is an interpretable model that can handle both classification and regression tasks. 4. Random forest. This is an ensemble learning method that leverages multiple decision trees to improve accuracy and reduce overfitting. 5. Naive Bayes. This is a probabilistic classifier based on Bayes' theorem. It is particularly useful for text classification and tasks with many features. 6. Logistic Regression. This is a powerful classification algorithm that models the probability of the binary outcome. It is known for its simplicity and interpretability. Model training. The dataset is divided into 2 distinct parts, a training set and a testing set. The training set, which is a substantial portion of the dataset, is used to train the machine learning algorithms. The testing set is utilized after the algorithms are trained, allowing us to assess their performance on new and unseen data. The experiments are conducted on a computer equipped with hardware specifications that include an 11th generation Intel Core i7 processor, 32 GB of RAM, a 1 TB solid-state drive for storage, and an 8 GB dedicated GPU for accelerated computations. The software environment is configured with relevant programming libraries and dependencies necessary for implementing the algorithms and conducting the analyses. Hyperparameter setting. Hyperparameters, which control the behavior of our machine learning models, have been carefully tuned for each model. Our tuning process involved systematically varying hyperparameters, such as learning rates, kernel types, and tree depths, to maximize predictive accuracy and generalization. For evaluating the model, we use the following metrics to evaluate and compare the performance of these models. Accuracy, the proportion of correct predictions among the total number of predictions. It measures how well the model can classify the instances into default or non-default classes. Precision, the proportion of correct positive predictions among the total number of positive predictions. It measures how well the model can identify the default instances and avoid false positives. Recall, the proportion of correct positive predictions among the total number of actual positive instances. It measures how well the model can capture the default instances and avoid false negatives. F1 score, the harmonic mean of precision and recall. It measures the balance between precision and recall and gives more weight to low values. The performance of different machine learning models for credit default prediction can be summarized as follows. Support vector machine model has an accuracy of 89%, a precision of 0.90, a recall of 0.89, and an F1 score of 0.83. Decision tree model has an accuracy of 94%, a precision of 0.94, a recall of 0.94, and an F1 score of 0.94. KNN model has an accuracy of 89%, a precision of 0.87, a recall of 0.89, and an F1 score of 0.88. Logistic Regression model has an accuracy of 89%, a precision of 0.90, a recall of 0.89, and an F1 score of 0.83. Random Forest model has an accuracy of 92%, a precision of 0.91, a recall of 0.92, and an F1 score of 0.91. Naive Bayes model has an accuracy of 22%, a precision of 0.86, a recall of 0.22, and an F1 score of 0.22. Among these models, decision tree has the highest accuracy, precision, recall, and F1 score, while Naive Bayes has the lowest values for these metrics. Based on the results, we say that the random forest model shows relatively high accuracy, but its performance might be skewed due to an issue with precision and recall of class bad loan. The decision tree model demonstrates excellent performance across all metrics, with high precision and recall, leading to a high F1 score. KNN showcases good overall performance, especially in terms of recall, which is essential in identifying actual credit defaulters. The SVM and Logistic Regression models yield similar results with decent accuracy, precision, and recall values. And finally, the Gaussian Naive Bayes model struggles due to imbalanced class distribution, resulting in low accuracy in F1 score. Conclusion: we have conducted a comprehensive comparative study of machine learning models for loan classification. Our analysis focused on evaluating the performance of several models on the dataset from a reputable financial institution in Bangladesh. The comparative study aimed to identify the model that best addresses the institution's loan classification needs. Through rigorous experimentation and evaluation, we have gained insights into the strengths and weaknesses of each model. This study will inform our decision on the most suitable model for real-world deployment. Some of the references are given below. Thank you for your attention.